So hello all, welcome to the second video in the series of Introduction to Writing User Material Subroutines for Elastoplastic Applications in ABAQUS. In the last video we saw about the software prerequisites, that is what are the softwares we need to install in order to implement user subroutines in ABAQUS. We saw apart from the ABAQUS software itself, we saw that there are two other softwares we needed to install. One is the Visual Studio and another is the Intel compiler. And we also saw in the last video how to link both these softwares to ABAQUS. So in this video we will be looking into some basics of UMAT subroutines, and we will also try to implement a very simple UMAT subroutine involving 3D isotropic linear elastic material behavior. So let us proceed. So why UMAT? The question may arise. So UMAT is nothing but is a short form for user material. So what UMAT basically does is it allows us to implement any user defined mechanical constitutive behavior of a material in ABAQUS. So if we have a material behavior which we need to implement, but none of the existing material models in the ABAQUS library can accurately describe the material which we need to implement. In such a case, we go for writing a user subroutine to describe the mechanical constitutive behavior of the material. In ABAQUS Standard, the user defined material model is implemented in UMAT, while in the case of ABAQUS Explicit, the subroutine used is called as VUMAT. So we will be majorly dealing only with UMAT, since we are going to deal only with ABAQUS Standards. So this flowchart here highlights the role of UMAT in a typical ABAQUS FEA. So here we can see that from the start of the step to end of the step, there are various steps. So first, once the step has started, then the start of the increment happens. So inside the increment we may have multiple iterations depending on whether the equilibrium is achieved or not. So once the iteration starts, the input strain components are calculated based on the strain displacement relations. So once this input strain component is calculated, the next step is the element stiffness matrix and loads are defined. So in between these two steps, this is where the role of UMAT comes in. So the input strain components is given as an input to the UMAT. Apart from that, we have to define some material properties. We will be seeing how to define these material properties soon. And apart from that, there are also some solution dependent state variables which can be defined in the UMAT. So this also we will be seeing later. So once the UMAT inputs are defined, then the UMAT we will be able to calculate the following outputs. So we saw that the input here is an input strain components. From strain we are able to get the stress components. So how we are able to get the stress component, that depends on the UMAT code which we are implementing. So what is the material behavior which we are trying to implement in UMAT. So apart from stress components, we see that there is one more output which is UMAT is required to provide. This is called as tangent stiffness matrix. So for people who are aware about finite element analysis and its working, so generally there is while element stiffness matrix is being updated, so it consists of mainly two components. One is the strain displacement matrix, which we call as a B matrix, and another is the tangent stiffness matrix, which we call as generally call as C matrix. And our element stiffness matrix is generally the integral of B transpose into C into B over the domain. So we can see that this tangent stiffness matrix plays a role in the element stiffness matrix. So this is also one another output which is expected from UMAT. Other than that, the solution dependent variables which we had initially defined in the UMAT, they can also be updated and they can also be viewed in the result. So once these UMAT outputs are given, we are able to define the element stiffness matrix and the loads. So in case if UMAT is not present, what is this step which is performed by UMAT is performed by the ABAQUS material library itself. But since we are going for UMAT, this function is performed by UMAT. So once element stiffness matrix and loads are defined, So then we need to solve the matrix equation for the element. Here we need to check for the convergence. So once the convergence is achieved, then we go for writing the output. If the convergence is not achieved, we again go for a new iteration, and similarly we try to repeat the steps as till the time the convergence has been achieved. So once the convergence has been achieved, we are able to write the output, and next is to check whether it is the end of a step. So as I said, a step may have multiple number of increments depending upon how we define our FEA problem. So if it is the end of the step, then we go for the next step, or we go for the next increment within the same step. So this is how UMAT plays a role in the typical FEA flowchart. So some general guidelines before going into seeing further more about UMAT. So for writing user subroutines in ABAQUS, Fortran 77 conventions are followed. So as you might know, Fortran is a coding device. So Fortran 77 conventions are followed. One can also follow C conventions, but I generally follow Fortran 77 convention. So I also recommend that people who are following this video also do the same. So I would recommend that some kind of working knowledge of Fortran 77 is will be useful for UMAT writing. So one important point about UMAT subroutine is that we are concerned only with the development of the material model. So material model in the sense we have some strain input as we saw earlier, and we need to get a stress output and the tangent stiffness matrix. So this is the only objective of UMAT. We are not going into the development and maintenance of the AC model, as in we are not going to work upon different types of elements, how the stiffness matrix is getting solved. All those things we are not worrying. When we are writing UMAT, we are worrying only about the material behavior. So when we have some material point in our domain, the material behavior associated with that point is only the cause concern for UMAT subroutine. So, and as I said earlier, the main outputs expected from UMAT subroutine are the stress components at the end of the increment. The consistent tangent stiffness matrix are Jacobian, and the solution dependent variables. So these can be defined, updated, and written as outputs. So for further information about UMAT subroutine, here there is a online ABAQUS documentation. I have provided a link. So if you are interested about learning more about this UMAT, you can click this link. So once you click here, this will get redirected to your ABAQUS user subroutine documentation. So here you can see there are many user subroutines defined. So there are various types of user subroutine depending upon our purpose which we need to use for. So UMAT, as I told, it is to simulate the mechanical constitutive behavior of a material, the user defined. So here you can see some overview, then different informations are provided, and the interface, and what are the variables to be defined. We will be seeing some of this in our presentation also. So this is there. So next, coming to the UMAT interface. So this is the how every UMAT code will look like. So you can see that there is a header which is provided, and there is a body, and then we end the subroutine. So this header will be common for every UMAT subroutine that we are going to write. In this case, as I told, we are going to look out for writing a 3D linear elastic material behavior in isotropic. So this header is common for every UMAT, whether it is a linear elastic behavior or a elastic plastic behavior or a viscoplastic behavior, whatever it is. So this header is common. So there are many variables which are listed in this header. So some of the variables we will be looking in this video. some other variables as and when we we write UMAT for different applications. As and when we encounter these variables, we will be looking those. So as I said, there is a header and there is a body. So this body is what we are going to implement. In the sense, we are going to code it. So user coding to define DDS DDE, which is nothing but a tangent stiffness matrix. This is stress, and these are the state variables. So other terms are also mentioned, but these are all related to energy terms. So we will not be looking into these terms right now. Our objective for this video, especially for the 3D linear elastic application, we'll just define these three variables. Once the coding is done, then we end the subroutine. So as I told, there are many variables. We'll try to get familiar with certain variables now. So you can essentially divide the variables into 4 main types. So I'll just switch on the laser pointer. So the first one is parameters which are available by ABAQUS to UMAT. So ABAQUS defines certain parameters and gives it as an input. So that is the first type. Second type is parameters to be calculated and updated by UMAT. So we saw that in the interface. So we have to define certain variables, right? So DDS, DD and stress, we can say that these comes under the second category, which means we have to update and give back to UMAT. Third is parameters entered through ABAQUS model definition and sent to UMAT. We'll be looking at this. The fourth one is the solution dependent state variables, defined and updated by the user in UMAT. So apart from these 4 types of variables, we can also declare new variables in our UMAT and we can update them. So when it comes to the variable names, the scalar variables are represented by single names. So we cannot use the numbers or symbols to represent, like lambda or mu, we cannot generally use. So we have to represent it by names like this, which contains of letters. So example, if you see here, so there are many variables like NDI, NSHR, NTENS. We will be looking at these soon. So these represent scalar variables. So one-dimensional arrays are vectors. They are represented by the name, followed by the dimension in brackets. So for example, quads bracket 3 represents that this is a one-dimensional array with 3 elements inside it, and this is vector is called strand with NTENS. So depending on the value of NTENS, that will be the size of this strand array. So two-dimensional arrays are represented by name followed by the dimensions. So here there is only one-dimensional array, so it can be either a row or column. So that is a number of elements in that row or column or whatever. So here we have to in 2D arrays we have to specify the row and the column. So row comma column is the convention. So here DDS DDE bracket NTENS comma NTENS. So this is how we represent the different types of variables in UMAT. So we will just look into the 4 types of variables which is specified. So parameters available by ABAQUS to UMAT. Some select examples. So we saw there are certain variables like NDI, NSHR, NTENS. So what does this mean? So NDI refers to the number of direct stress or strain components at the material point. NSHR refers to the number of shear stress or strain components at any material point. And NTENS refers to the total size of the stress or the strain component. So which means that it is the number of direct components plus the number of shear components. So if you look at an example, for a general 3D case, we know that there are 3 normal stress or strain components and 3 shear strain components. So we can list them as your sigma 11, sigma 22, sigma 33. These will be your normal components. The shear stress components will be sigma 12, sigma 23 and sigma 31. So this is for the general 3D case. For a simplified plane stress model, we have 2 normal components which are the in plane and 1 shear which is also in plane. The out of plane components do not exist. So in the in plane components we have 2 normal and 1 shear. So which means it will be like if we say our plane is xy or 1 2, we can say that sigma 11 and sigma 22 are the normal and sigma 12 is the shear. So this is about these 3 variables. Other than that, we have certain other some variables like stran. Stran depicts the array containing the strain components, the input strain components at the beginning of the increment. Dstran refers to the incremental strain. So this is the absolute value of the strain at the increment beginning. So this refers to the increment of strain. So if I say this is epsilon, it's an array containing like epsilon 11, epsilon 22, epsilon 33 and so on. So this will be delta epsilon 11, delta epsilon 22, delta epsilon 33 and so on. So here we have something called time. So this is a one-dimensional array with two elements, of which the first element depicts the value of the step time of the beginning of the current increment. Time 2 depicts the value of total time. So if a analysis contains multiple steps, so we have something called step time and total time. So time 1 depicts the step time and time 2 depicts the total time. So for example, if you have analysis of two steps with each step being 60 seconds each, so let us say that we are in the second step and the step time at that particular instant is 30 seconds. So our time 1 will be equal to 30, while time 2 will be 60 plus 30, which is 90. So this is the time variable. D time represents the increment time. So which means for a particular increment which is going on, there will be a value of time increment. So D time represents that. So this is the first type of variables. The second type of variables is the parameters to be calculated and updated by UMAT. So we have mainly two types of variables here. One is the stress variable. So this is nothing but the array of stress components. So UMAT gives the it passes in the stress vector at the beginning of the increment. So we have to update the stress value based on the material behavior and then pass it on back to the UMAT at the end of the increment. So NTNS means stress has the size of the stress array is NTNS, which means depending on your application, if you have a 3D case, then you have 6 components of stress. So DDS DDE is nothing but the Jacobian or tangent stiffness matrix. So in matrix terms, this is what Jacobian essentially means. So it is nothing but DDS DDE of I comma j is equal to d delta sigma I by d delta epsilon j. In other words, DDS DDE defines the change in the ith stress component at the end of the time caused by the change in the jth stress component. So which means that let us say DDS DDE of 1 comma 1 means d delta sigma 1 by d delta epsilon 1. If it is DDS DDE of 1 comma 2, this means d delta sigma 1 by d delta epsilon 2, so on and so forth. So this is the tangent stiffness matrix. So these stress and tangent stiffness matrix are the parameters which need to be calculated and updated by UMAT. So there is another type of variable called as the parameters which are entered through the ABAQUS model definition and which are sent to UMAT. So we have some material property to be defined. For example, in a typical elastic case, we may need to define Young's modulus and Poisson's ratio. But how are we going to define them in the UMAT? They are done with the help of this props variable. So n props refers to the number of properties which we are going to define. So when defining the model through ABAQUS, these properties are entered, parameters are entered in the property module. So the last type of variables is solution dependent state variables. So state V is the name of the variable. N state V refers to the number of state variables which we are defining. So state V is nothing but an array containing the solution defined state variables. So similar to other variables, so ABAQUS passes in these parameters at the beginning of the time increment. So these have to be updated in the UMAT and then these values have to be returned as the values at the end of the increment. So one thing about state variable is, apart from certain primary variables like primary field variables like displacement, strain, then secondary variable like stress, etc. So these can be viewed in the visualization module of ABAQUS. Apart from this, you can also try to view the state variable. So whichever variables are defined as state variables, these results can also be viewed in the visualization module. So this is about SDVs. So as I am describing about various types of variables, this will become more clear as we look into the UMAT coding. So before going into coding, there is also one more thing. This is nothing but the conventions. So As I told earlier, in the stress and strain arrays, we have two types of components. One is the direct components, another is the shear components. So, the convention of ABAQUS states that direct components are stored first, followed by the shear components. So, which means that in a 3D element, stress will have 6 components. The first 3 components will be your direct components in this order, particular order, sigma 11, sigma 22, sigma 33, and the shear stresses are stored in this particular order, which means sigma 12, sigma 13, and sigma 23. So this is the order which is followed. If it is for a plane stress element, then we will have only 3 components in total, 2 normal and 1 shear. These are all the in-plane components. For plane strain and axisymmetric, we have 3 normal and 1 shear. The out of plane shears are 0. There is a in-plane shear of sigma 12. In case of strain, one thing we need to know is the shear strains are stored as engineering shear strain and not as the tensor value of shear strain. So which means that your shear strain is stored in this format. Gamma ij is equal to 2 times of epsilon ij. So which means if you have a shear component of 12, gamma 12 will be equal to 2 times of epsilon 12. Another note which is very important while dealing with UMAT is, so in case UMAT is used for elements with reduced integration, so people who are aware about the integration in ABAQUS, there is an option called as reduced integration while defining the element. So when this option is used, when UMAT is used for such an element where reduced integration is selected, we need to define the hourglass stiffness by ourselves while defining the element mesh. So this we do not need to do when we are going for ABAQUS material library inbuilt, but when we are using UMAT for element with reduced integration, then we need to define the hourglass stiffness. Alternatively, there is an option of enhanced hourglass stiffness which can be selected. So this is some conventions. So now we will go into the example which we want to implement in the UMAT. So this is nothing but a 3D isotropic linear elastic material. So the governing equation is pretty simple. So you have a stress array and you have a strain array, and you are going to link them through the elastic modulus matrix. So this is the stress array, this is the elastic modulus matrix, and this is the strain array. So sigma is equal to C times of epsilon. This is nothing but your generalized Hooke's law for 3D. So we see that there are 2 parameters, lambda and g. These lambda and g are called as Lamé's constants. So lambda and g are in turn related to 2 other constants. One is the Young's modulus and other is the Poisson's ratio. So lambda value is given as mu into E by 1 plus mu into 1 minus 2 mu. G is equal to E by 2 into 1 plus mu. So E is the Young's modulus and mu is the Poisson's ratio. So now we are going to implement this in UMAT. So some steps I have listed here. So in case of the elastic problem, the tangent stiffness matrix which I have described earlier is same as the elastic modulus matrix. So our DDS DDE is nothing but this matrix is by itself. So this is in the case of linear elastic. However, this may not be the case in the case of elastoplastic applications where there is a plastic deformation also involved. For this example though, the DDS DDE matrix, which is the Jacobian or the tangent stiffness matrix as I mentioned earlier, is the same as this matrix. So that is there. Other than that, as I told, there is the array called props. These are how we are going to define the material properties in the UMAT. So Young's modulus and Poisson's ratio will be defined as props 1 and props 2 respectively. And as I told earlier, DDS DDE matrix will be defined as the elastic modulus matrix. So how we are going to get the stress is, we are going to do the matrix multiplication of this DDS DDE matrix with the input incremental strain. So this will give the input incremental stress for that particular increment, and this is added to the stress at the previous value so that we can get the updated value of the new stress components. So this is the step which we are going to do. Let us see how we are going to do. So I will go to the Visual Studio now. So once you open it, you have to click continue with code, without code. So just go for file and open, click this file. So I have the file already written. I would have named it 3D linear elastic. I'll open it and I will explain through this file how we are going to implement the elastic linear elastic for 3D. I'll close this also, and I'll close this one also. Yes. So as I told earlier, this entire stuff which you have written here, this is the header. So if you go back to the presentation, so this is the header which I have listed. So beyond this header, there is the body which need to be coded by us. Okay. So there are many variables. Some of these variables I would have explained to you in the presentation. So other than this, we are also going to define certain variables which we are going to use in our code. So we are listing them here, and as per our Fortran convention, I am listing them as real variables with 8 floating points. So that is this here. So another thing which we need to look at when we are writing Fortran code in this what you call Visual Studio is all our lines start from column number 7. So this is line number 1, column number 7. So if I try to push this in before, so what happens is the subroutine which was earlier highlighted in blue color, the blue color goes away. This means that this line is not counted in the code. So what I need to do, I always need to start from column number 7. This is applicable for any Fortran 77 convention. At column number 5 or rather column number 6, there are some numbers listed. This, if you are familiar with Fortran 77 convention, this is nothing but once you have comma and you need to continue in the next line, you just list a number and then continue. This means that this line and this line are continuous. So if I keep the line over in this bracket, you can see that the closing brackets both are highlighted, which means that this is a continuous line. Why I write like this is, if I keep on writing over here, you see that certain lines start to become green color. So Fortran has this 77 in Visual Studio has this property that beyond the line number 73, which I have highlighted here, it cannot take in the lines. So I have to delete this. So see that after when I put comma and I have to continue, I put some number in the column number 6 of the next line, and then I start my code, continue my code. So here if you see, both the brackets are highlighted, which means that this entire line is a continuous single line. So when I write, so after this, when I write something C, so which means that this it is similar to the commenting. So it can either be C or it can be exclamation mark also. So this you can if you want to write some comment in green color, so you can use this C and write this. If you are not using C and if you are maybe writing somewhere here, this will be counted as a line in the code, and when you are implementing this code, you will get errors. So for that, you add a C as the line. So next line is nothing but include. So in C there is a include stdio.h. These are the standard library. Similarly, this is ABAQUS parametric. So this is this thing needs to be included in all the UMAT codes. So these are the header which I am talking about. So there are some predefined variables which some of which we looked at earlier. So these are mentioned with their dimension in the brackets, so which also I mentioned earlier. Apart from this, from here our real body starts. So I am 4 variables I am now including here. I am listing. So one is my Young's modulus, one is my Poisson's ratio, another is lambda, and another is G. So as I told earlier, we cannot represent variables using symbols, so we need to write them in letters. So these are some comments which I have included. So this is a UMAT for 3D isotropic linear elasticity, where I am giving I am defining two properties. One is the Young's modulus and other is the Poisson's ratio. So here I am defining them. E is equal to props 1, mu is equal to props 2, and lambda I am defining in terms of E and mu. Lambda is equal to mu into E by 1 plus mu into 1 minus 2 nu. So when you are writing this formula, make sure that the brackets are proper. And another thing, when you are writing 1 and 2, make sure that you are writing 1.0. If you write as 1, it may take as an integer, but mu is not a integer. So to maintain the consistency of variables, mu is a real variable as we mentioned here, and 1.0 should according to Fortran convention, it will be taken as a real variable. If I just mention 1, it will be taken as an integer. So to maintain the consistency, I am putting 1.0. G is equal to E by 2 into 1 plus mu. So lambda and G I have defined. So next I am going to define the elastic stiffness matrix. So in my case, as I told earlier, NDI is the number of direct components, which is 3 in this case since it is a 3D, and NTNS is equal to 6. So if you look at the matrix, what I am doing is I am defining from 1 to 3, which means that this is row 1, this is row 2, this is row 3, this is column 1, this is column 2, this is column 3. So for in this I am concentrating, I am filling the elements. So lambda plus 2g for the diagonal elements, and rest of the non-diagonal elements will be lambda for I is equal to 1 to 3 and j is equal to 1 to 3. So similarly here I am starting a do loop. K1 is my variable, K1 is equal to 1 to 3 since NDI is 3, and K2 is also equal to 1 to 3, and first I am filling all the variables with lambda. So all my 1 to 3 will be lambda, and later I am particularly fixing on upon the diagonal elements and writing it as lambda, replacing it with lambda plus 2g. So which means for K1 comma K2 ranging from 1 to 3, all my elements are lambda first, and then for the diagonal elements alone, where K1 comma K1 I have given, so it will be lambda plus 2 times of g. So all the diagonal elements will be replaced by lambda plus 2g instead of lambda. So this is for 1 to 3, and for 4 to 6 we can see here the diagonal elements alone are g. So here I can say from do K1 is equal to NDI plus 1, which is 3 plus 1 4, 4 to 6. All the diagonal elements K1 comma K1 alone I am fixing as g. If I am not defining any element, it will be taken as 0. So I don't need to specify 0 for other elements, it is automatically taken care of. Suppose you find this to be confusing, what you can also alternatively do is you can individually DDE as DDE of 1 comma 1 is equal to lambda plus 2g plus 2.0 times g. You can define element by element, DDS DDE of 1 comma 2 is equal to lambda. So you can also do element by element, but since it will take long lines of coding, and when our matrix is much bigger than this, here it's a 6 cross 6. Suppose in other cases when any matrix when you are defining, it will take more number of lines, then you cannot define element by element. So you need to use some do loop, and you have to strategize how we are going to define the matrix. So first here I concentrated along only this 3 cross 3. I defined all the elements as lambda. Then for the diagonal elements alone I replaced with lambda plus 2g, and for this I fixed from 4 to 6 all the diagonal elements as g, and the rest all elements are 0. So once we have defined the DDS DDE matrix, now we have to just multiply the DDS DDE with the input incremental strain. Why I am doing input incremental strain is, so we have the stress value which is from the previous increment or previous step, we get that value, ABAQUS provides us, and that we are updating with some incremental change. So delta sigma is equal to C times of delta E. That is what we are doing here. So DDS DDE into delta strain. So D strain we saw, which is nothing but the array of incremental strains which ABAQUS provides us based on the displacement strain relations. So stress is equal to stress plus DDS DDE into D strain. So this is how we have updated the stress. So now we have updated the stress for this particular increment, and that is the end of the subroutine. So we can see that it's a very simple subroutine. Apart from the header, which is common for all, we have listed 4 variables which we are using in our course of our code. We define the elastic properties through props 1 and props 2. Since we require only 2 properties for our application, we have just listed 2 properties, and we updated the elastic stiffness matrix, and then we calculated the stress. So this is the code. So now what we are going to do, I am going to implement this code in ABAQUS. So how that implementation is done, I will explain step by step. So first I have the ABAQUS here. So you have to go for the standard explicit. I assume that people who are following this video series will have some working knowledge of basic ABAQUS stuff, like how to provide displacements, how to provide boundary condition, how to provide load, how to mesh the components, how to create the parts, how to provide material parameters, those things. So that I assume. So what we are going to do is we are going to create a very simple cube part now. I'll click the create part. So before creating the part, I'm going to set the work directory. So default you have in the temp. So here I'm going to create a new folder. So this will be linear elastic. Okay. So this I'm going to select, and I'm going to give the OK. So I'm going to create a new part, which is nothing but let my name by part as cube. So it's a solid and deformable. So I give continue. A small square with a 10 cross 10 dimension, with centered around the origin. I do. Once I draw the square, I click this into, and I click done. So this is my solid, which is going to be this is the 2D drawing which is going to be extruded, and I give a depth of 10. So which means that our cube of 10 cross 10 cross 10 is now ready. So after the part, I'm going to give the property. So here only the UMAT specific properties, how you need to give, I will explain. So once you click the create material, let me name this as linear elastic. So since this is the behavior which we are going to implement. So if you see here, in general, there is an option called user material. So we need to click this. So you see that mechanical constants are there. So in our UMAT, we saw that there are 2 properties. One is Young's modulus and another is Poisson's ratio. So I give Young's modulus as it's 200 gigapascal. I am mentioning it in megapascal. So 200 into 1000 megapascals. And Poisson's ratio is 0.3. So this is approximately some steel value, you can say. I give the OK. So another part which I have to say here is, there is something called as DEP VAR. So this is nothing but number of dependent variables. So we saw there is something called as state variables, right? So it will be listed as state V. However, in our UMAT, we do not have any state variable defined. This may not be the case always, as we see in subsequent videos where we are going to deal with elastoplastic applications. There we need to define certain state variables. So there we have to define the state variables, but in our case we are not going to define anything. So we will just delete this. So delete this behavior, and we are going to define only the user material properties. I click OK. So once this material has been created, I have to assign this material to a section, homogeneous section. I click the continue, OK, and then this section I am going to assign it to this part. I uncheck this, I select this part, give the done, section 1, OK. So now it has turned into green color, which means the section has been assigned. So assembly, I am going to just create an instance. Okay, so the coordinate system has been established. The step, I'm going to create a new step. I'm going to switch on the nonlinear geometry. Incrementation, I'm going to give a fixed incrementation. My maximum number of increments, I can give some any high value. This is just for safety. Increment size, I'm going to give 0.01, which means my total time period is 0.01, which means that 100 increments I am providing for this step. Once step is created, here we do not have any interaction. We go directly to the load. This phase, I'm going to go for a uniaxial tensile, which means that I'm going to fix this phase first. This phase I'm going to fix it. It's nothing but in ABAQUS terms it is the N-caster. I'm arresting all the degrees of freedom. This is along the x-axis. So one phase has been arrested and other phase I'm going to give some displacement. So this is load. I have to give displacement. I select the displacement. I select this phase. Let me say since it is a 10 cross 10 cross 10, I'm going to give some 1 mm of displacement, which means that my strain will be close to 0.1. So 0.1 for an elastic case, which will be too high, you can expect stress to be in thousands or in 10,000s, 10 power 4 terms basically. So this is not the practical case, but just I'm only implementing a linear elastic behavior. So it doesn't matter whether it's practically true or not. So we are just going to implement behavior as defined by UMAT, and we are going to verify it later. Okay. So I have just created a displacement of 1, or maybe not 1. 1 will be too much, I think, for elastic. Maybe I am going for 0.1 probably. Even this will be because usually the elastic strain at the yielding point will be something around 0.02. But anyway, let us say 0.1 is our displacement. So sorry, I am going for the mesh. Now I am going to create a single element only. I have to go for the path. I have to approximate global size. I am giving it as 10 because I am going to mesh the entire cube as a single element. So you can see that the nodes are created only at the corners of the cube. So now I click the done, and here I am going to mesh the part, which means that the color has changed, which means meshing has done. So here I am going to assign the element type. So it is a 3D stress standard linear. We click off the reduced integration. I already mentioned before in the presentation. So when we have reduced elements with reduced integration, we can use the option of enhanced hourglass stiffness. But in our case, let us say we are not going for it. We uncheck this option. So we have a 3-dimensional brick element with the 8 node. So C3D8. So we give the OK. Once the meshing has been done, now I have to do the job. So before going for the job, I'm going to check what are my field output requests. So I remove contact, force let me keep as it is, displacement is fine. In strains I'm going to remove all the plastic stuff because our it's an elastic thing. So we will have only the logarithmic strains. The stresses are okay. And one more thing is, when you have a state variable which result you need to take in ABAQUS, there is an option of selecting solution dependent state variables in the state option. So here I am going to uncheck it because I do not have any state variable defined in my UMAT. So the field variables are fine. So now I am going to submit the job. So how the job we are going to submit is, let us say it's a job 1, or I am going to remake it with UMAT. Okay, I think there should not be any space. So with UMAT. So in the general, I am going to select the user subroutine file which is going to define the material behavior. So I click here, I go to desktop, where I have the file defined. So I'm going to the desktop. So here there is a 3D linear elastic. So I have already explained to you the code. So this code is going to drive the material behavior. So I select this code, I click OK. So the job has been created. Now I'm going to submit. So let us wait for the job to complete. So since it is just a simple elastic, I think it will not take much of time. It will be completed soon enough. So I think the job has been completed. We go for the results. You see that the stress has been computed, 2.412 into 10 power 3. So which means that this is going into the thousands. So this may not be practical, but we have implemented a 3D linear elastic situation. So this is without, as I told, we have just predicted through UMAT. So how this result is correct or not, how do we check it? So since it's a 3D linear elastic behavior, we already have a standard ABAQUS inbuilt model. So we are going to do the simulation through the inbuilt model and check the results and compare with the UMAT result. So that is what we are going to do next. So before that, in presentation I would have listed here. So validation of UMAT. So verification of UMAT is usually done with a small input file, which is of single element. So what we have to do is run some benchmark test with different types of prescribed displacement. It could be a uniaxial, tensile or compressive. It could be multi-axial, which is a biaxial or triaxial, or it could be a simple shear case also. And compare this test result with analytical solution or standard ABAQUS material models. So if possible, so if the verification is successful, then we know that our UMAT writing is correct. So that's what we are going to do. We are going to simulate the same situation without UMAT. So I'm going to create a new database, model database. I save this as with UMAT. So now I'm going to create the same part again. So the 10 cross 10 cross 10 part. In property, I am going to now define as usual. So elasticity, I am going to define the elastic properties, 200 gigapascal, which is 200,000 megapascal, 0.3 Poisson's ratio. The same value I am giving, but without the UMAT. Here I am renaming the material as linear elastic. Property, defining the section, assigning the section to this part, assembly, creating the instance, step, creating the same step as created earlier, switching on the non-linear and making it as fixed. This I am giving some higher value for safety, and increment size is 0.01. Same stuff. Let me check it once more. Yes, okay. I give the same load as previously. First I am going to encaster the face along the x-axis left side, and right side I am going to give a displacement of, I think I gave 0.1, same 0.1 I am going to give here. Okay, so this has been done. Meshing, same single element mesh. I am going to give the mesh global mesh size of 10. give OK. I messed the part. Same thing, I remove the reduced integration for consistency. Job, I'm going to just create a new job. I'm going to name it without UMAT. So last term was with UMAT. Here I'm not going to define any user subroutine file at all. I'm just going to give OK and I'm going to submit. Before submitting, let us check the field variables. As earlier, I'm going to remove all the plastic parts since we are totally dealing only with elastic, and contact also I'm removing because we do not have any contact. So job, I'm going to run this job. So we are going to check whether we are getting the same result as the result we got in UMAT. We are going to check the results of the stress. Okay, now we are going to check the results. So this is without UMAT. So 2.412 into 10 power 3. So here in the same visualization, I am going to with UMAT. You can see that I have got the same result. So the same results I have got. So this means that the UMAT which we have written is correct, and we have hence we have verified the correctness of our UMAT. So I hope this video was useful to understand how to create a simple UMAT for linear elastic. So in the subsequent videos we will be seeing some more examples. So thank you for watching this video.